Okay, so hopefully audio is being recorded too. So in this question, we have a survey of Alberta students used to estimate the percent of students who participate in school and non-school athletics. So that's what we see in the Venn diagram. And we want to know the odds in favor of a randomly selected Alberta student who participates in school athletics. So odds in favor of participating in school athletics. So see what you can figure out from that. And I will do attendance while you work on this question. So Armand, you just read my mind, I guess, and I forgot what my mind was. That was the next question. So we just did this one. Question number 4 is slightly different though. Let's go over number 4, and that'll give you some more time to do the rest of the page. So anybody have a strategy that they think might work? Or you thought would work, but you don't know where to go from it? You got started? Well, what it looked like some people were trying was figuring out what's the probability of getting a king or a queen. So maybe I should use the proper notation, king or queen, and then the other one. So I'll give you a hint, this isn't going to work. So if you started writing this, just stop. I'm going to write it down, and I'll show you why it turns into a problem, but then I'm going to erase it. So if we thought of this, and we thought of that formula, we'd say, what's the probability of king or queen. So that's something that I could calculate. And then the probability of the other given the king or queen. So the probability of getting a king or queen is not too bad because there are 4 kings, 4 queens, there are 8 in total. So 8 out of 12 are either a king or a queen. But the problem comes here. What's the probability my next one is going to be the other one? Well, I guess this could work, maybe. Because whatever one I picked here, there are only going to be 3 of them left, right? So I could say there are 3 out of 11 of whichever one I drew first. So I think maybe this does work. I told you it wasn't going to work. I thought it wouldn't. But now I'm thinking it does. Because I thought of a different way to do this question, and we're going to get the same result, I believe. So our notation looks kind of goofy, but are there questions with our process there? We're okay with that? Okay, so this would give me, if I was to simplify it down, 2 11ths, I think. Question? Sorry, can you say that again? Uh-huh. There would be 4 queens left. Oh, 4? Oh, that's what you're saying, because I want the other one. Oh, yeah, that's worth a candy. Which isn't the answer I'm getting from the other one, maybe. Well, let's just see. So that was a good correction. Thank you. I will give you a candy for that. This should be, we'll fix this. So whatever one I picked first, I didn't pick, so there's still 4 of those out of the 11 left. Okay. So this should be, what was this last one? 4/33. So I think this will be 8/33. Okay. I'll just group this. It's readable. And just move it out of the way for the moment. So here's another way we could have done it. We could have said, well, what's the probability I get a king and then a queen? Or means add the probability of getting a queen and then a king. So we do end up with the same result, the 8/33. So either way would work. But then notice how I also considered the possibility of thinking of this as a counting methods question, where I did a 4 choose 1 gives me the king, and the 4 choose 1 gives me the other one, over the 12 choose 2. So I get 1 king, I get 1 queen, over choosing 2 cards out. And either way, we should end up with the same result. So this did work. That's great. And I'll just leave this here for a moment, and I'll give away candy while I remember. Do I owe anybody else candy from the last few days? I don't believe you, but thank you for volunteering. I owe you candy? This I could believe. Why do I owe you candy? Okay. And Simran agrees. Do you have anybody to vouch for you, Umer? Huh, yeah. I still don't believe you guys. I don't know. Oh, well, then the substitute should have given you candy. I do want to get rid of all this by the end of the week, but I'm just not convinced. I'm sorry, but Earn it again. There we go. Okay, questions? No questions? Okay, I'll give you some more time to work on 5, 6, and 7. Okay, can I get your attention, please? And gentlemen, return to your seats. Sanders, that's not quite your seat. I know you almost blended in, but not quite. Okay. Question number 5. If you listed them out, you have 3, 6, 9, 12, 15, 18. So there's 6 numbers between 1 and 20 that are multiples of 3. Okay, so 6 out of the 20, there we go. Now, for number 6, if I draw a tile, I don't look at it, but you show it to a friend and they tell you it is a multiple of 3, then you know it's one of those 6 tiles, right? So, the total number of possibilities that you could have are the 3, 6, 9, 12, 15, 18. So that's why the denominator is only a 6 here, because you know it has to be one of those 6 tiles, but only one of them is also a multiple of 4. So this is different than number 7. Number 7, you draw a tile, you don't look at it. What's the probability it's both a multiple of 3 and a multiple of 4? Well, here's what we could do. We could use that formula and say, what's the probability it's a multiple of 3 on my first draw, times the probability it's a multiple of 4 given it's a multiple of 3 on my second draw. So that's one way we could think it through, and we get 1/20th. So I wanted you to see how the formula works, not the only way to do the question. So what we could have done is we could have just listed them all out, and we said, oh, between 1 and 20, there's only one number that's both a multiple of 3 and multiple of 4, the number 12. So 1/20th. We could have done it that way as well. So both ways work, but again, handy to have more than one way to do a question, because then we can do it one way, we can check it another way. Tanvir. Okay. Questions with number 7? Nope. All right. Next page. And I'm just going to pause because I think I see something there that I don't want to see. Okay. So now we're getting a little more practical. In the previous questions, really we're just playing games. This question is a little more useful, as in, a jam manufacturer knows that in the case of 100 jars, typically 5 jars will contain less jam than what's shown on the label. So we're going to use a tree diagram to determine the probability of all the possible outcomes if we draw 2 jars at random. Okay, so here's how we'd use a tree diagram. We would say, well, first I should define my term. So I'm going to say L is going to mean less volume than the label states, which means L prime is not less. So we like L prime because then you have at least as much jam as the jar says it's going to contain. So does this ever happen in real life? Well, yes. Like if you go to 7-Eleven and you're going to buy a Coke or something, you can look through the bottles and you can see that there are some that have slightly more than other ones. And of course, you pick the one with more volume because you want all the caffeine you can get or something. So there is some variability when jars or bottles or whatever get filled by machines or even by people. So here's what we have. When I make my first draw, I have two possibilities. Either it has less jam than it says, or it has as much or more. And then, given that first outcome, the second jar, again, less or as much or more, less jam or as much or more. So the way we use a tree diagram here, and you'll see that I drew in kind of these branches, and I'm going to write probabilities along those branches. So for my first jar to have less jam, we're told 5 out of the 100 jars will have less. So the probability that happens will be 5 out of 100. The probability it doesn't have less will be 95 out of 100. So you'll notice both of those add up to 100%. One of those outcomes has to happen. So now I start thinking about the next part. So suppose my first jar had less jam than the label said. What's the probability my second jar has less jam than the label says? Well, one of those 5 is already gone. So now there are 4 jars with less jam, but I'm drawing from 95 jars because I already took one out. As I look underneath at the next line, so suppose my first jar had less jam. What's the probability my second jar has as much or more jam? Well, there's still 95 jars that have as much or more out of the 99 that are left over, because again, this first jar is already pulled out. I'll have you fill in the next two. And then as we calculate what's the probability of A and B happening, it's the probability of A times the probability of B given that A already happened. And then the same idea for the next one, we're just multiplying the two branches together. And you can probably predict for the bottom half of this tree as well. It'll look like this. I'm going to scroll up again here, and then I'll come back down to this. So this probability tree, just like this probability tree up there, where here we filled it in with the numbers from the example, and then down below, we've done it in more general terms. So one more thing I want to look at in this page, but first we have a question. Yes? Uh-huh. Okay. You're good? Okay. The last thing I want to look at is how the notation kind of fits in with Venn diagrams. So here, this is true whether events A and B are independent or dependent. Okay, so it's always true, but just to have this notation in a Venn diagram could be helpful, kind of again in a general sense. The first is probability of A happening and B not happening. So we're inside the A circle, outside B. The middle green part, probability of both events happening. And then on the right, A doesn't happen and B does. And then outside, neither A nor B has happened. So again, we get those 4 outcomes for those 4 sections of the Venn diagram. Just like, and I'll scroll down again in a moment, here we had these 4 outcomes listed on the right-hand side. So that's the connection between a probability tree and the Venn diagram. So they're both ways of describing all the possible outcomes when we have 2 events happening. Sometimes one is going to be more useful than the other, but sometimes you can just use, for example, the tree to fill in the Venn diagram. Okay, the next page, is it a check your understanding question? It is. So I'm going to let you go ahead and look at that, because again, as I look ahead, I see I'm showing some work that I don't want you to see yet. So I need to clean up that page. Okay, so in this question, what's the probability somebody has this disease? Question tells us, hello? Tanvir, put your phone away. Sorry, somebody said? 0.2. So 0.2% have the disease, which means 99.8% don't have it. So if this person tests positive, was the test correct or incorrect? It was correct because they have the disease and it tests positive. So positive means the result shows you have the disease. And how accurate is this test? Well, it said up here, it's 95% accurate. So this will be 0.9, well, let's write it as a percent because that's what I did on the other ones, 95%. So if it tests negative, then that means the test was wrong, and that'll be 5% of the time it tests negative. Now I'm writing these in as percentages. When I do my calculation, I will want them to be in decimal form. Okay? So I'll change those to decimals a little bit later, but for now I'll just write it out this way. So suppose somebody doesn't have the disease. What's the probability they test positive? 5%, because that means the test was wrong. And we know that 5% of the time, the test is wrong. So here we have 95% of the time the test is right, which means somebody doesn't have the disease, and the test tells them they don't have the disease. So that's how we would fill in the tree diagram for these probabilities. I'm just going to replace them with the decimal forms to use in the calculations, and that's what we would have. Any questions? So hopefully it makes sense. It's not simple, but hopefully it's clear as in where we're getting each probability from. So what does each outcome mean? So this first row means somebody has the disease and they test positive, so the test is correct. So those I will start dragging out here. Probability has the disease and they test positive, which means we get a correct result. The very bottom branch was also a correct result because the person doesn't have the disease and the test told them that they don't have the disease. And those middle two outcomes are situations where the test is wrong. So here somebody has the disease, but the test tells them they don't have it, which is not a situation you want to be in. But that's how testing is in real life. And then the next option, you don't have the disease, but the test tells you you do have it. You don't want to be in that situation either, but it's a better situation. You feel horrible because you think you have this disease, but you actually don't. So life will be fine. It's just you have a lot of stress in the meantime. So kind of the second row here, X and negative, you feel fine because you think you're okay, but you're actually not. So which situation would you rather be in? Well, you want a correct result, if at all possible. So as we just look back at these probabilities, I'll scroll down again in a moment. If I look at these two results, they're wrong. And if I added those probabilities together, I get 5%. Oh yeah, that's what we were told in the question. 5% of the time, the result is wrong. And if I added the first and the last, I'd get 95%, because 95% of the time, the test is correct. So given that much and given those numbers, how would you fill that into a Venn diagram? I'll give you a couple minutes and then I'll drag out my Venn diagram. Okay, that wasn't much time. But before I get to the Venn diagram, I actually want to come back and talk about this just for a moment. So of these 4 options, you really don't want to have the disease, but it's even worse if you have the disease, but the test tells you you don't. So this is, I would argue, the worst place to be in this probability. And notice that's a pretty low probability. That's like 1 in 10,000. So 1 in 10,000 people has the disease, but the test isn't correct. You don't want to be that person, but that's not too bad. Like if only 1 in 10,000 is incorrect that way. But here, notice we have like almost 500 people in 10,000 who are told they have the test, but they actually don't. Well, you don't want to be there either, but what's going to happen? Either you're going to start getting treated for this disease, a treatment that you don't need, or they may do a more expensive, more accurate test. So likely, kind of the first layer of testing is something that's not super expensive, and so it's not super precise. Because the more precise a test is, the more expensive it probably costs to develop it. So do the less expensive test first, narrow it down. They'll have a number of false positives, but then they can do a more expensive test on fewer people. And then they can narrow it down even further. So practically, that's kind of how it looks. Here's how my Venn diagram ended up looking. We have those 3 parts. So either I have X or I'm tested positive. So those are the 2 circles. So the 2 events have to do with the same 2 events that we had up here. The person having the disease is one event, or not, and then getting the test result is the other event. So I chose to go with having the disease and testing positive. You could have done not having the disease and testing negative. So we had a few options. But then taking the numbers from the table above, this is where I'd fill them in. So again, this person has the disease but doesn't test positive. So that's the 1 in 10,000. This is the one where they test positive but they don't have the disease. And then here's where it was correct because they had the disease. Here it was correct as well, people who didn't have the disease. And there we have conditional probability. Yes, team. So, once again, tomorrow's going to be a work day because this is challenging stuff and I want to give you feedback as you go. So feel free to do a little bit at home, but we'll take all of tomorrow's class to practice. If you have not written the test from chapters 2 and 4, then expect to write it on Friday. I don't have a clear picture of who's written it and who hasn't, but you should know. So if you still need to write that test, plan to write it on Friday.